Am I on? Yeah. Thank you.
Whoever is outside, you can ask them. Start.
I'm waiting for the board to get dry.
You're not going to ask me questions, right? Yes. Then I can sit here. See, that's the only place which remains empty so far. So I have no choice but to sit here.
Okay, so far what we did can be summarized in few sentences. In the first day, we taught a mixture of polymer chains. That's what we did. And then using random mixing approximation, we derived the free energy of mixing, which went something like a two component system. We had something like this. So in this, we had temperature as one of the variables, and chi that depends upon temperature and chemical mismatch between these different components. But this is a mean field description.
So, Muthu, one question. So, when I have a polymer and I'm trying to write down a flow dynamics theory, the counting of states is a really difficult challenge there. So, is it like people assume that it's a mean field, like they are not seeing each other, excluded volume interaction, and these things are ignored when computing the entropy, change in entropy?
That's not true. They do. We do accounting for conformational entropy.
But,
right.
But yeah, I mean, I would like to know that a bit.
Are you sure? Okay.
So we should discuss.
We could discuss that either offline or today a little bit. Okay. Let's keep going. Right. Okay. So we did this here, as Sandeep is saying. We did not account for any fluctuations. No fluctuations. We placed them randomly, and I counted number of ways of placing them, and that gave this entropy of mixing, which always favors mixing. And here we took into account only nearest neighbor interactions between type 1 and type 1, between type 2 and type 2, between type 1 and type 2. We did not think in terms of backbiting, for example. A part of this chain may undergo a conformational change, right, and then come back and interact. That correlation, long range correlation, we did not account for. That was in the first lecture. Right. In the second lecture, given this premise, we calculated the power of this mean field theory was the ability to calculate this thermodynamic stability of the system. So temperature, this is related to 1 over chi as a function of volume fraction of the one of the components. We had a coexistence curve like this with a critical temperature Tc and spinodal curve like this. Inside this is completely unstable. Between the envelope of this yellow curve and red curve, we have metastability. That was what we did in the second lecture. And we also showed the criteria for the spinodal decomposition, the limit of thermodynamic instability, the second derivative of free energy, that we calculated here with respect to the composition is 0. That was the criterion for this spinodal line. But on the other hand, at a given temperature and given composition, it will undergo phase separation to give me two phases, two daughter phases, one phase here, another phase there, in such a way the chemical potential of one component is same in these two daughter phases, chemical potential of the second component is the same on the at the same two compositions. Okay, that's what we did. We also, based on this, we also looked at some fluctuations in here about the critical temperature. That means, right, the very fact that we have fluctuations means that there should be additional terms. Nevertheless, we invoked this Landau-Ginzburg free energy functional, not worrying about the interface. We assume that it's going to be an interfacial tension, but the leading term of that lambda free energy is second derivative of this delta F by kT with respect to phi, which becomes 0 at the red point. And from there, and in fact what we did was we wrote this red curve. We had something like 1 over n1 phi 1 plus 1 over n2 1 minus phi 1 minus 2 chi. This is equal to 0 at this point, and this we call it to be A, and we wrote this to be 2 chi critical, chi spinodal minus chi. Since the chi is the reciprocal of T, this went like T minus T, let me call this to be T spinodal, T minus T spinodal. That's the way it went. Right. So, A is like a quench depth or the distance or temperature, distant temperature from the spinodal point. Okay, that's what we did in the second lecture.
Sorry, chi should go 1 over T, right?
Yeah, T will go like, yeah.
Okay, I mean, okay.
Sure, let's do this. 1 over T minus 1 over T, yes, that's equal to T s minus T, right. All right. Yeah. It's related to T minus T s. And we also argued that as you approach this point, right, the scattering intensity goes to infinity. That's because it goes like 1 over A. We worked it out. This won't train Zernica, right, or free field theory if you listen to other talks, right. So, this the intensity will diverge, and then depending upon, because the second derivative of free energy is going to be 0 here. This is my second derivative, that's going to be 0 at the red curve, spinodal curve. So, when we approach like this is going to 0, second derivative, reciprocal of second derivative, this is Einstein theorem, right. Reciprocal of second derivative is a scattering intensity. This is called a sum rule, that's what he showed, and then Woods and Zernica demonstrated by using experiments. Okay, so that's what we did in the second lecture. And the third lecture, what we did was to bring a little bit of respect to this polymer. The polymer molecule is not just a bunch of spheres just randomly mixing. As Sandeep was trying to ask me the question earlier, it has a correlation. Okay, and how did we treat this correlation? The way we did that was to consider, to begin with, let me write for a Gaussian chain, then we can generalize this. For a Gaussian chain, if you have a chain like this, random walking chain, the radius of gyration of this chain goes like square root of n times monomer length divided by 6, root of 6. Okay. That is like a ball of wool. The typical radius of this coil goes like this. and we wrote down in general this to be like n to the nu, proportion n to the nu, in this particular case nu is equal to half for a Gaussian chain. Then what we did was, I need to use this in the rest of the talk. What we did was, this was due to Debye. What he showed was the structure factor which we measure in experiments, right, scattering intensity, and hit somewhere here, it scatters off, and when they get scattered, then there is a constructive interference, and then you measure that intensity. That scattering intensity as a function of the scattering wave vector k, which I defined in several times, k, that is proportional to the structure factor S of k, that is proportional to 1 over n, that is equal to 1 over n, summation over I, summation over j, e to the I k dot the position of the ith monomer minus position of the jth monomer. But the important thing is, this turns out to be, this is averaged out, scattering, I am averaging because this is all dancing around. This turns out to be equal to 2n k to the 4 e to the 4 e to the minus k square. You have it in your notes already, so you don't have to copy it again. Something like this. But the important thing that comes out of this is, this goes like n to the 1 minus the 3 k square r g square, sorry, 3 k square r g square with 3 here, plus etc., or 1 over k square. K is scattering by vector. When k is large, I am looking inside the coil. When k is small, I am looking outside the coil. If I want to know the size of the polymer and the mass of the polymer, my probe that I am going to look at, this one should be, the probe length should be larger. Otherwise, I will not be able to measure. If you want to measure the size of me, if I have a yardstick only this much, that is not going to measure my 1 meter height. I need a yardstick which is bigger than this, right. That means k should be small. So that is what we do here. This is when k times Rg is smaller than 1, I can get Rg, measurement of Rg, which I told you. That's the way people measure. That's why in every laboratory, commercial instruments, everything, they use this idea. On the other hand, if I go to length scales shorter than radius of gyration, k Rg is greater than 1, then I am interrogating the substance in this short length scale, and then I get 1 over k square. Okay, what if I of k goes like 1 over k square, that means the density, this one is density concentration correlation function. Therefore, the density variable from one point and from the other way, if you do the Fourier transform, rho of k goes like 1 over k square. Let us do the Fourier transform this rho of r. Let us say I go to somewhere here and look at how the monomer density is changing with the distance. It goes like 1 over r. Okay. Exactly. That means the monomers are correlated and they have a long range correlation. Just almost like having a charge, electrical charge, and the field is felt far away, even though, right, the density is falling off like 1 over r. This is why we say the topological correlation of a single chain is long range, or the chain connectivity itself results in this correlation. Okay. Accurately describe my free energy of this mixture.
What was the density?
Local density, yeah, density, monomer density.
How is it if rho goes up as 1 over r?
Say it again, please.
If rho goes up over as 1 over r, how does it ensure long range?
How is this what?
How does it ensure a long range correlation? I would have thought that C of r going as 1 over r would be.
Yeah, local concentration, right? Let me draw a cartoon here. So if I have a chain like this, right, and let us say this is the radial distance r. If I plot monomer correlation function, that I choose one monomer here, what is the probability I am going to find another monomer at certain radial distance r? If I plot this, that is going to go like radial, right? R 0 is going to go like this. Okay, for short distances, you know, you will not see anything. So maybe I should have plotted it will go like 1 over r. Far away, you will not see any monomers. Very close to the location you chose, the density will be high. But then when you go away, it's going to fall off like 1 over r. Compare this with a globule. If you had a globule folded protein, then the density profile would look like this, flat, until the radius of imagine a steel ball of steel, up to the radius it will be flat and nothing outside. In contrast to that, you have 1 over r like a long range correlation. Okay.
This is density correlation.
This is density correlation. So I am writing rho 0, rho r average, but a rho 0 I am just picking one point. Okay. But this is important to know how correlation function is taken, how they are correlated. Right? The density is falling off. But in general, this is 1 over r is for a Gaussian chain. But in general, depending upon the interactions, which we did a derivation in the last lecture, right, depending upon the correlations, you will have a different value. Nu does not have to be half, it could be a different number. Typically in good solutions where you have extra volume interactions, that becomes like a 3/5 for approximately 3/5, for example. And we also said this 1 over k square actually is 1 over k to the 1 over nu, fractal dimension, and fractal dimension is 1 over nu. Okay. Therefore, this r then would go like 3 minus 1 over nu in general. When nu is equal to half, Gaussian chain, that becomes 2, 3 minus 2 is 1, and it is not necessarily 1 over r. It would be a different power law depending upon the conditions. If they are charged, depending how much salt you have, they will be different. Now, going back to an earlier comment, suppose it is collapsed object. If it is collapsed object, nu is equal to 1/3, right, because Rg goes like into the 1/3, Rg cubed, which is volume, is proportional to mass. When nu is equal to 1/3, you see 1 divided by 1/3 gives me 3, 3 minus 3 is 0. So, it is a number, there is no correlates, it is highly correlated until the radius. That is my blue curve. This corresponds to nu is equal to 1/3, this corresponds to nu is equal to half, and somewhere in the middle depending upon your experimental conditions. Okay. And somehow we need to bring this up, and we know how to do it. It is not somehow, we do, the technology I introduced in the last lecture. You write the Hamiltonian and work it out, and then you will calculate the consequence of these structures. Comments? Any question?
Yeah, this rho of r, this is density profile or this pair correlation?
They are the same. They are the same. So, we write a rho of r as concentration at some location C, concentration R, right? That is proportional to rho of r, right? This is, you fix some average density corresponding to the same. With respect to that, how the other one is varying with distance. Okay, so, right? Any other comments? Okay, this is what we did so far. Any other comments?
So, question, so this structure factor is always proportional to rho k density in.
Yeah, it's a rho k. Yeah, rho k square. It will turn out density. The structure factor is a rho k square, rho square, monomer correlation function, because one rho will come from one sum, summation over I, e to the ik dot ri. That's your density in Fourier space. Right, and then the other one is complex conjugate of the density in Fourier space. So, rho k, rho minus k average is your structure factor. Right, the density, right? The density, I write in and erase it. Rho of k. Let me write rho of r. Rho of r is equal to summation over I in this particular case of 1 to n, a delta of r minus ri. Right. If a monomer is at the location R, it will count to the density. If it is not there, it won't count. Okay, what is rho of k? Rho of k is a Fourier transform of this summation over I 1 to n dr e to the I k dot r and delta of r minus r I. That's equal to do the integral, right? Delta of r, wherever you see r, you put it in, get rid of this summation over I from 1 to n e to the I k dot r I. That's what appeared in here, e to the I k dot r I summation over I. That's rho k. And the other one is a rho minus k, because a negative sign here, because it cannot be imaginary. The structure factor cannot be imaginary, it should be real. So you take the complex e to the I k dot r I, complex conjugate of that e to the minus I k dot r j, you take the product and that your scattering intensity. That's the way we do. Yeah.
So how semi-flexible?
How what?
How semi-flexible nature of the polymer affects
Well, you could guess it from here. Semi-flexible, I did not do the derivation. Of course, we have the technology to do the derivation. Nu would be something like 0.8, right? Because 0.6, 3/5, roughly 0.6 is the external volume chain, and the rod is nu is equal to 1. R is related to n, proportional to n as 1. So semi-flexible chains would be somewhere between 0.6 and 1. Depending upon the extent of semi-flexibility, right? So it could be 0.8, 0.9, 0.7, right? But it's never 1. It turns out it's never 1, unless it's really a short double-stranded DNA. Okay, so what I like to do today is to equipped with all this information, I want to go down below the coexistence curve. So here is a homogeneous phase, right, and I want to go down, right, into this. That means I'm going to quench the system underneath this yellow curve, and I can quench into the unstable region, or I can quench into the metastable region, depending upon the composition. And I like to address what is expected if I quench here or I quench there. Okay. It turns out, depending on where I quench, the system evolves in a particular way. If I quench here, it is going to evolve in one particular way. If I quench here or quench there, it will evolve in another different way. But nevertheless, at the end, I will get the same answer, same result. The same, suppose I quench to this temperature here, right? I will always get these two daughter phases. Whether I quench here, here, it does not matter. But the pathway of reaching the final state would be different. Okay? There are two distinct pathways. And that's what I want to address it today. Okay. Before I go further, right, I need to know a little bit about the free energy, because if I am going to quench a system, the way the system is going to evolve depends upon the free energy of the system. But so far I wrote only the free energy only for this part, only mean field part, and somehow I had to bring this part into this one, going back to the earlier question, right? And I started doing this, but we ran out of time. So let me summarize what we did before. I think I'm going to erase this, right? Dilute solution. When I make the concentration to be higher, then I have interpenetration. So there is a concentration, polymer concentration, above which this interpenetration is going to take place. And that concentration is called overlap concentration. This is for C greater than a concentration called C star. This is overlap. That's the concentration at which the chains are about to overlap between them, they are about to interpenetrate. For concentrations less than that, the chains are going to be alone, more like a dilutes, they are lonely. But when you keep on increasing the concentration and when you reach this limit, then they begin to interpenetrate.
So only one chain, if it penetrates with the others, we will consider it as a penetration or condensed system.
No, I think this overlap concentrations for the whole system, all chains are interpenetrating.
How do we define this interpenetration? Like, when do we call two chains are interpenetrating?
It's not two chains, right? So imagine I have many chains, right? I have n chains. So let me take a box, right? There are n chains, right? So this is one chain in here with some radius gyration. Another chain is in here. Another chain is in here, on and on. And here another one, on and on. Another one, on and on. And another one, on and on, right? When the concentration, right, roughly there are prefactors which one has to work out. If the concentration is such that there are n chains and there are n segments, all right, there are little n number of chains, n segments, okay, that's the total number of monomers divided by, right, volume of the chain. In such, it is the n chains times the volume of this, volume of each chain, that is say Rg cubed, apart from 4 by 3 pi and everything. I am not writing down, all right, let me put it like this. Okay. So when I take a volume Rg and they are essentially compact, right, in this concentration, then the total volume is proportional to the volume of each coil times the number of chains, and the concentration defined in terms of mass by volume. That mass is, there are n monomers per chain and there are little n chains, and Rg we know, Rg goes like n to the nu. Therefore, this C star, this will be the C star. So, C star would go like n power 1, n power 3 nu. So, this goes like n to the 1 minus 3 nu roughly, and prefactors can be obtained. Okay. That is the definition of C star.
I was asking because if we suppose these are linear thread-like things, if they are
Yeah.
Still like for concentration less than this C star also, they could interpenetrate like two threads going like this.
That's not the way we define, right? You know, because this is a coil like, right? This is a coil, right? More like a ball of wool. All right. You are not talking about a rod like. If it's a rod, right? If it's a rod, then you have liquid crystallinity, there are also other complications, right? We are not talking about that. This is a flexible chain which has a certain radius, right? And then when you bring multiple chains together, they are going to be packing until they begin to interpenetrate. If you increase the concentration more than that, then they'll begin to interpenetrate.
So, like if this tunes us that this ball has, like you said, the density profile falls off as 1 over r. So it will retain its spherical kind of shape throughout
Until it interpenetrates.
until it.
Yeah.
Okay.
All right. Do you go to market to buy things, vegetables?
Yes.
You do? Do you buy apples?
Yes.
Take a bag of apples. What do you see? Apples.
Yeah.
They are all packed.
Yeah.
Okay. Now take a large number of flexible polymers.
Yeah.
You think they are going to be like that?
Mm.
No, they will interpenetrate.
Yeah.
Why?
That
Why? Why would they interpenetrate?
because the ends can go.
Because they will gain entropy.
Yeah.
They are able to adopt enormous number of conformations by interpenetration, right? Unlike apples, you just pack them, right? Imagine yourself made of a bunch of balls. In contrast with polymers, right? Polymers are able to interpenetrate. When they are able to interpenetrate, why? Because they gain lots of entropy. That's favorable.
Yeah.
So, yeah.
What I was saying is that interpenetration is possible even for less concentration than this C star, because the threads could go from one sack of wool. The threads could.
That's not the way it works, because the translation entropy that can avoid and go and explore the whole volume is more. When in the very dilute solution, right? You know, here is one polymer chain, another polymer chain. Why would it try harder to interpret? Instead, it will wander around. Only when you increase the concentration, they cannot get anywhere except to interpenetrate and gain entropy. Right? So that's why we define this. Anyway, since we are kind of slow, now today is the last lecture, right? right, Sandeep? Right. So yeah, but still keep asking. I can hang around for extra time if you have stamina. Okay, so what I did was I showed in the last lecture, when you have interpenetration, then the interaction between segments, right, between two segments, which is responsible for this nu, that gets screened. All right, we talked about Edwards screening, right? The extrude volume interaction gets screened. We had a nice discussion with Devayan this morning. Right, they get screened. So what is the consequence of this? So in a good solvent, right, in a good solvent, the chain is swollen, so that the nu is 3/5. But when I increase the concentration in the same solvent, same good solvent, when I change increase the concentration, the chains begin to interpenetrate, and then when I measure experimentally with the neutron scattering, measure the radius of gyration of one labeled chain, same chemistry, same solvent, but in a dense system, it's a Gaussian chain. That means that the interaction, the intra-chain interaction now is screened by interpenetrating other chains, and therefore this is like between me and Devayan, right? Our interaction is being screened by this gentleman.
By Sandeep.
Huh?
By Sandeep.
Sandeep. He doesn't want to. Doesn't want me to talk to him. He screens, right? If he's not here, we talk. Same thing. So it's a screening, and then we did a calculation. Yeah. Sorry.
So for overlap concentration, you are considering here all the chains are like homopolymer kind of. If they are not, if they are heteropolymers, then say like as you are saying, the screening effect or electrostatic will come into play. Say negative, positive, they might interpret more maybe in a lower concentration as well. Right?
It's possible. It's entirely possible. So yeah, it is entirely possible. But it's entirely possible. So right, when you write like this, the chain has not seen yet. Okay, I'm still writing this configuration, right? I have not written this yet. So this is kind of an indicator of when that's going to happen. The effect that you are talking about is going to happen constant higher than this, not below. Right? Okay, so what we showed was this, the simple argument we did, and I did not mention the technical name for that. The technical name is random phase approximation. And you will see this in any field. So what we did was we took all the tree diagrams, tree structures, interactions, right? As a consequence of this, what we found was there is a correlation length. That is, if I have this something like this, then I have a distance. I have distance in this interpenetrating system. There is a distance here along which the monomers are correlated, just like the correlation that I am talking about. So instead of 1 over r, now it's screened only over that distance. I have correlation. Beyond that distance, the other chains come into play, and that 1 over r correlation is wiped out. In fact, what we showed was the effective interaction delta r goes like v, right, and 1 over r e to the minus r over c. That's what we wrote down. Something I'm not writing all the 4 pi's and everything. Originally, you would have 1 over r. That 1 over r interaction is now converted into something Yukawa type, screen interaction type. And clearly, this interaction is extrude volume interaction only up to a distance comparable to c. For distance larger than that is zilch. It's not going to c. Okay. And then we showed, in the last lecture, we showed that c goes like, for neutral polymers, it went like a concentration power minus half. For charged polymers, it went like c to the minus quarter. That's what we did in the last lecture. Now, this is RPA. But when you have this, the tree like approximation we made may not be enough, right? it may not be enough. So, you need to do proper calculation for strong fluctuations. Instead of this, suppose with strong fluctuations, if you have this, it turns out, which I am guilty, right, C goes like C to the minus the 3/4, and we know the numbers in here, and for charge systems it goes to C to the minus half, and we know these numbers, that number we know, that number we know. Okay. All that I am trying to say, you have to trust me that there exists a technical methodology, which is what we do in the other campus, right, tomorrow and day after, day after tomorrow, and then you can calculate these correlation lengths for these highly fluctuating topologically correlated systems. Okay. And why am I even taking a burden to mention this to you? The reason is, when I look at the free energy, right, this free energy by KBT, I have the mean field part, part, which we did there, plus a fluctuating part. That fluctuating part goes like 1 over 24 pi. The pi always creeps in, you guys know that, right? There is a magic pi c square b, sorry, c cubed b, where this c is the correlation length. Okay. This is, you can take it as a theorem, and it is derivable, and there are references where you can derive, right, and it is a mathematical beauty to derive this, right. If you are interested in bringing mathematics, theoretical physics and mathematics to beautiful polymer physics, soft matter physics, living matter, if you want to do that, you will enjoy doing this calculation. So, the fluctuations are contributing, and this C depends upon the concentration of the polymer, right. That is a volume fraction related to volume fraction of the polymer of some kind. So, therefore, when I write the free energy of the system, it depends upon the concentration of the polymer and of the chi parameter and all the electrostatic interaction going into this early part, and then plus this also depends upon Beerem length, which I mentioned. All those things will come into play. So, that is our starting point in composition of this coexistence curve. Right. I can make the statement the chemical potentials are the same, and I showed the calculation for the simplest case how to do the calculation, but when you have these things, and it may be necessary to do numerically, okay, because of the it is not an analytical function, right. This goes like C to some fractional power, so you may have to do analytically. Okay. Accuracy in comparing with the experiments. Okay, that is a roadmap of this is your starting point, and you use the thermodynamic principles of equality of chemical potentials for the coexistence curve, and the second derivative of free energy going to 0 with respect to composition to dictate a spinor curve. Okay.
So if I just one thing, that the fluctuation is in psi, which has only the concentration part. Temperature is not there.
Oh, temperature appears there. Yeah.
I mean the way you have written, temperature is coming only in delta.
The prefactor. Yeah, there is a prefactor here.
Oh, there is the
Prefactor. Yeah. And for the Coulomb cases, it is the Beer length. The dielectric constant appears here. Dielectric constant depends on temperature, that appears there. That is why you may have to do numerically for a realistic problem for biomolecular condensates. You have to do it properly. You have to first learn this and execute it for properly for your particular system, and then compose it. Yeah.
So if I, rather than polymers, if I consider just particles, point particles, in that case, how does this get modified? Or more importantly, like for the kinetics, what features will polymer give you, like if nucleation growth and all that I do not get from a particle?
Yeah. Okay. This is an excellent question. Could you please wait? Yeah, could you please wait? So, the question is what's the distinction between particles and this one, right? In similar to the previous question, if it's a particle, nu is equal to 1/3, right? Nu is equal to 1/3. So, where is C star then? Nu is equal to 1/3, right? It doesn't depend upon molecular weight at all, because that C star is not small numbers. C star is really the whole system. random closest random packing 0.63, whatever that number is, right. That is what happens, right. But more importantly, when we look at the phase diagram, how does the topological correlation appear in distinguishing the kinetics of simple particles to the structured particles, structured molecules. And that is the reason why I am preparing myself to, I am reminding you folks, that is the reason why this part I reproduced, because we are going to use this to bring about what is happening there. All right. Okay, so
just one question. This what strong fluctuation mean? Topological strong fluctuation mean?
it means more like still there is, let us take polymers and water. That means still the polymer chains can adopt lots of conformations.
Those fluctuations.
Yeah, that is highly fluctuations. But if you increase the concentration more and more, there is not enough volume for solvent, there is not enough solvent, and then they fluctuate, but they do not fluctuate that much. Okay.
Going to dilute basically.
No, it is too concentrated. In dilute is a heavy fluctuation,
yeah.
and then increase the concentration, high fluctuation, and then no fluctuations, right. And RPA traditionally is valid for weak fluctuations in all fields of condensed matter physics, right. All fields of condensed matter physics, RPA corresponds to weak fluctuations. In fact, when we make measurements, you observe this result in the semi-ideal conditions, and you observe that result in very high concentrations when you do neutron scattering. Similarly for charged systems. Okay.
I have just why are you calling topological correlation? What is the
It is a
meaning
chain
of
connect.
topology?
Oh, that's a good question, right? Because it has a dimension, right, and it's a connectivity.
Yes, dimension and connectivity, and even if you destroy something, that will be still will be like that.
Yeah, it's a permanent topology. Yeah, it's not like some creation and annihilation operators chopping the chain and making them again, right. Like unlike there are lots of worm like micelles, they would not be topological because they make and break. This is a nomenclature, right. Yeah. People sometimes do not want to call topological when they simply say chain connectivity, but it is indeed topological for the reasons that we talked about.
Because in a topological, generally we find some kind of a invariant number, right, corresponding to that.
Talk about invariance, yeah.
So what is there may be some invariant number corresponding.
Well, if you have one chain here and then bring another chain, how many times it winds around, right? That's a topological invariant.
That will be like whatever you do, it will be.
It will be there. Yeah, that is more like an Aharonov-Bohm effect. In the quantum, it's an Aharonov-Bohm effect, and that's what we will have here. How many times? So if you have a chain which is being knotted, right, you could use Alexander polynomial as an invariant or Jones polynomial as an invariant, and tau. That's a topological constraint. That's the reason why people use this. At least I use this. Okay, so who wants to? Let's take a vote. You want me to do this one first or this one first?
Either you one is first.
You one is the first. Since you are the first to say and you is the first. Okay. So, yeah. So the first, the early bird, catches the worm, right? That's the phrase. Okay. So I'm going to erase this. Is that okay? But I want to keep that one. And I'll erase this too. I'll keep that one. Okay, so let me go here, right? Let me go somewhere there, and then I'm going to quench like this. I want to ask a question of what will happen, right? Somewhere here at the early before I do the experiment, I go there, and I want to write concentration of the polymer or your entity at some location R to be equilibrium value without any fluctuation. So plus a fluctuation, as we introduced in the last lecture, day before yesterday, right? There is a mean field value and there is some fluctuation. Now that fluctuation gets bigger and bigger when I go down in temperature, right? That's what we talked about, and that's that result. And then you measure that fluctuations using the Wundt and Zernicka methodology, scattering intensity methodology. That's what we did. Okay. when I suddenly quench it, I will have that fluctuation here, right. But that is unstable. What it wants to do, it wants to make two daughter phases with one phase with that composition, another phase with that composition. So something is going to happen. So in order to understand this, let's look at the kinetics. That is d phi r by dt is equal to negative divergence of flux. This is the conservation of mass, right. This is conservation, negative gradient of flux. What is flux?
So that's the chemical potential. You are going to write it.
Okay, a gradient of chemical potential, negative sign, and there is a coefficient before. I mean, professor is not allowed. Anybody knows what the coefficient is? Okay, you can say mobility. We call this to be Onsager coefficient. Okay, Onsager was a great genius. You guys know this, right? The guy who solved a two-dimensional Ising model exactly, only his brain and paper and pencil. Onsager coefficient. In simpler cases, that becomes a diffusion coefficient, and this equation is called Fick's diffusion law, Fick's law of diffusion.
So when you say special cases, it becomes a diffusion. Like when is it?
When there is no cooperativity, only one particle is
One
moving.
particle. Yeah. And we know a relationship between this and a corresponding single. I don't know how to think about that, but is a
Corresponding what?
like a single particle.
You just wait. Wait. Okay, so what is chemical potential? I told you, right? Chemical potential is d delta f by d n1, right? So this is more or less, this is proportional to d delta f by d phi 1. Okay. Okay, so I could rewrite this, right? I could rewrite using this. I could substitute this expression phi of r into this, and let me work in Fourier space, because we always do scattering. When you do light scattering or neutron scattering, X-ray scattering, we work in the K space. That scattering wave, that's a Fourier transform, right? So let me work out the Fourier transform of this continuity equation, but take care of the linear response, only fluctuation part. What you get is a d psi k by dt is equal to, going back to this, negative times negative positive, and then I have this is lambda, there is a del square. The Fourier term to del square is a negative k square, therefore I get a negative lambda k square, right? And the gradient of that would be delta f in a Fourier space, maybe delta psi k. Okay, that's the equivalent of Fick's law, or non-equilibrium time evolution of fluctuations in general. And I also told you delta f in the last lecture by kBt is equal to half summation over k resolving very small times a psi k square within simple Landau-Ginzburg theory, without RPA, without doing very complicated calculations. And this is what I showed in the high temperature phase. Let's start there to begin with, and we will work out all the other consequences.
Kept up to the second order.
Sorry?
Kept in Ginzburg-Landau, you kept up to second order.
Second order, only up to second order. All right, and then A we wrote down to be equal to 1 over n1. I think we wrote down phi 1 plus 1 over n2 phi 2 minus 2 chi. Did I write down somewhere here? Maybe not. Yeah, here. Sorry, I forgot already. That's my A, same thing, and that goes like this. A goes like T minus the Tc. Right? I'm coming up from here, or if I come this way, suppose I come off S, subscript S, T minus Ts. Okay, so I could generally use a T minus Ts if you want, because at the critical point, Ts is same as a Tc. So the prefactor here A, not prefactor, the coefficient A, the leading term in Landau theory, is a measure of the distance of temperature from the spinodal temperature. Okay. And this is the interfacial term. I told you about kappa being an interfacial term. Okay. Now, this is the place, this is a time that I should pay respect to an earlier question from Sandeep, the distinction between particles and the polymer. Okay. Let us go to this one. If I have Debye structure factor like this, which has the k dependence, this must somehow appear in this expression A. It must appear. The reason why it did not appear here is we are taking k is equal to 0 limit, the thermodynamic limit. When k is 0, I am talking about infinitely larger system. Therefore, I can write down this expression. Okay. So, if you do this, right, if you do this in the context of RPA, let us do RPA, then the structure factor S of k, right. Now, for the mixture, now I am talking about structure but not one particular chain, it goes like this goes like 1 divided by phi 1 S Debye structure factor of the first component. Maybe I should not write, let me write I of k. No, yeah. This is for the whole mixture. This is for the first component k plus 1 over phi 2, the Debye structure factor of the second component k, and then plus minus 2 chi. So, this formula that I am writing here becomes generalized into this one, where S d1k is this expression. S d1k is this expression, and for the first component, degree of polymerization, number of monomers could be capital N1, radius gyration could be Rg1. For the second component, it will be N2, Rg2. So, in general, you could, I am not going to write explicitly, but you get the idea. So, you get this is my structure factor. You also know the structure factor is the correlation order parameter correlation function, right. Structure factor is, right, the average of psi k square, similar to we wrote a density correlation function, similar to that for mixtures, for intermingling mixtures, it will become average of square of this psi k. That is my structure factor. That you can calculate as a reciprocal of this. Okay. So, if you do, again I am interested in k small, right, because we are interested in thermodynamic phase transitions, right. So, k becoming small, k is becoming small. This turns out to be 1 over n1 phi 1 plus 1 over n2 phi 2 minus 2 chi, right. Then I can expand this S1 k. I already told you S of k goes like n1. Now, in this case, that's my n1, and then the denominator 1 minus k square Rg square by 3. So, I am going to do the numerator. I will pick a term k square. 1 divided by 1 minus will give me 1 plus k square. So, that will give me here, that will give me plus k square, and you can tell me Rg square goes like L square n1 divided by, there is a 3, Rg square 6, and then there is 3, that will be 18, and then I have here n1. I take this, right, this is going to be 1 divided by the square bracket. So, therefore, when I bring this to the right hand side, when k small, I will become 1 plus 1 times n1, right. You do this, then this whole thing is the denominator. What you get is k square n L square by 6, and there is a 3 here, and then 1 factor n will cancel, and that will give me this term. Just do the arithmetics. Similarly, for the other component. So, therefore, I could rewrite this n. Okay. Similarly, other component k square L square n2 divided by 18 n2. So, if you have particles, this will not come about, right, because the structure factor, form factor of a sphere is 1. There is no k dependence, right. There is really no structure. There is no k dependence, right. Okay, if that is the case, then what I have is taking this in here, this kappa this kappa, which is related to the surface tension, right, interfacial tension, that kappa is equal to, we are now deriving kappa based upon the structure of the polymer, and that's equal to, you can write, oh sorry, there's a phi 1, there's also phi 1 here, and this is phi 2. So what you have is 1 over 18 times 1 over phi 1 plus 1 over phi 2. Because I am comparing k square, because I am picking from the structure of the polymers components, even within RPA, I am picking a term which goes like k square. That means in free energy, that's square gradient term in free square gradient space. So therefore, I collect all the coefficients, it becomes like this. This is important because when you have a droplet, right, which we are going to see, the interfacial tension is going to play a role, because with the concentrations low, right. So you write phi 2 to be 1 minus phi 1. 1 minus phi, this is phi, right. If the concentration of the polymer is low, right, 1 minus phi is comparable to 1, this is 1, but this is going to dominate, this is going to be very large. So it creates lots of interfacial tension in the condensates, entirely due to entropic origin. Entropic origin, because we calculated how is this, how is that term coming about? That's coming about because of the topological correlation of the polymer chain. And that's the difference between particles and polymers. Interfacial tension is augmented by the topological correlation. Okay, given this, okay, that's the setup. Okay, so let me look at this one. How is this going to evolve with time? Okay, this is only with the linear terms here. I did not do anything else, right? Only with the linear term. So how is this going to evolve? That's trivial to do with the first order partial differential equation, simple differential equation. So if you do this psi of k, right, at time t, and psi of k at 0 time, and average it out. This is what I want to do. Why? This is what I measure. The structure factor that I mean, the intensity I measure now is a time dependent structure factor, time dependent correlation function of the order parameter, right. So that's what I want to calculate. How do I do this? So I can solve this simple equation, d psi k bring, oh sorry, this is equal to minus lambda k square. Let's do this calculation, and that is going to be equal to, right, given this, we take the derivative, function derivative, I have a plus kappa k square times psi k. Okay. So using this, I am taking the function derivative and I get that one. And that's a linear thing, because d psi k by dt is proportional to psi k. Therefore, d psi k by psi k, that's d log psi k, is equal to whatever I have here times dt, and integrate it out. If you do this, you get psi k square, this is equilibrium, times e to the omega k, some rate, times the t is exponential, where omega k is equal to minus lambda k square a plus kappa k square. That's it. If I am writing fast, you have to stop me, because I have a bad habit of writing quickly. Okay. Did I do it right?
So omega k is positive for all k.
Let's wait here. Let's do it. Let's do it. I'm going to plot omega k. Okay. Well, let's plot omega k. Okay. So omega k. So I'm going to erase it. I need space. Okay. May I erase this, please? Can I erase it? Yeah. Let's plot omega k. Okay, so Onsager coefficient, that's always positive. Negative sign, always negative. Square of k, positive. Kappa interfacial tension must be positive. K square is positive. Now let's look at A. A I wrote down to be T minus Ts. Okay. Now temperature is here. are here, temperature is here, and Ts is there. So T minus Ts is negative because I quenched it. Okay. So therefore A is negative when I quench it. A is negative, and this is positive, this is positive, this is negative sign, and this is A is okay. So let's look at small k. For small k, this is not going to be that important compared to A. For small k, this is not going to be important. Therefore, this is a negative number, and then another I have negative number, positive quantity. This is quadratic in k, negative, negative, positive, quadratic in k. So what happens is this is going to increase like this for small k. But for large k, this is going to dominate over this. This is going to dominate over that. That means this is positive times that's positive, there is a negative sign. So it's going to go like a k to the 4 with a negative sign. So it's going to go down, crash down like k to the 4. So what will happen? It has to turn around. Right? This means even in the weak fluctuation limit, right, we have a spontaneous selection of some rate of fluctuation growth. Right? So this is positive, 0, negative, and we can calculate this. When this is going to be 0, let me call it the critical value of k. That's going to be what? I think A over kappa square root. Okay, because this is going to be 0, right? Yeah, A over kappa square root. And when k, there is some number. This A depends upon the quench depth, and kappa depends on the interfacial tension, which in turn depends upon concentration. Okay. Given this combination of concentration, molecular weight, right, and quench depth, if I am looking at a large k means a small wavelength. Small wavelength is a large k. That's rate of that fluctuation, rate of growth of the fluctuation is negative. That means they are going to be killed. But on the other hand, for smaller k, less than this value of kc, that means large fluctuations, they are going to grow. That's positive. So according to this description, which is correct description, large wavelength fluctuations are cannibalizing smaller wavelength fluctuations. The bigger fluctuations, long fluctuations are growing with a positive rate. They are growing, and the other small wavelength fluctuations are decaying. Okay. This has lots of implications: sociology, economics, the way politics is run. And we know personally some of us are rich, some of us are poor, and there is zero-sum game, right? And you know how this happens. Right. So based upon this, you can work backwards to say, how could I become here instead of there? Intuition. You work it out. Take it as homework. Okay, so what's the consequence of this? Then I put this back in here, right? Then this fluctuation will grow. So I measure scattering intensity, I have kt as a function of k, and let's do at the different times. At the early time, very, very early time, right, omega k is going to be what? For smaller value of k, it's going to grow. For large value of k, is going to go down. So that means you are going to see an intensity like this. Only for because of positive, right? It will be intensity will go like this, because that's where you are seeing growth. But for higher values of k, they will not see any intensity. So you wait a little longer. Same thing will happen, but except now with longer, this t is larger than before, and it's exponential. A little longer, it'll go like this, and little longer, even higher intensity, it'll go like this. That means the peak position would not shift in the scattering intensity as a function of time. Peak position will be at one particular value, but intensity will be going like crazy. Okay. So if I plot I of k, maximum intensity, k max, right, no, let me not do that yet. Okay, let me do this.
So
Okay.
Muthu, again going back to the polymer versus polymer picture. So kappa will be impacted, as you said. So then essentially if kappa is much larger for polymer, then the RC, the position at which you cut, will be different between polymers.
Right.
So, and is it possible to now somehow detect in experiments where this polymeric feature comes out to be?
Yeah, sure. Of course, indeed. So you can shift. The phenomenon will be the same.
Yes, but
Right.
those are
You have designing ability to orchestrate the navigation of fluctuational growth. Particularly, Mother Nature plays this game with the biomolecular content. That's why there's a plethora of biomolecular condensates, and then with the small changes in sequences, everything, you can play magic. But at the risk of repetition, the burden on us, or the opportunity and also luck that we have, is to be able to do these things very cleanly, and then bring this picture and then decorate the sequences of the polymer and then go further. Because this is a ground floor. This is something that we must do first. I'm talking to younger people. We must do this first. Okay, and then are rushing to computation or modeling, whatever. Right? These are basic things. Okay, but now if you wait long enough, you will see peak like this. Okay, the maximum has moved to the left, because when the fluctuations are growing, I cannot afford it to be stuck only with the psi k square term, because now the magnitude of psi k becomes larger, the fluctuation becomes larger, therefore psi cubed term will be important, psi fourth term will be important, so I have to take that into account. And that is beyond the scope of these lectures, but if you do this, then eventually you get the ultimate phases. Okay. So let me plot k max as a function of time, logarithm of time. What will happen is, for early times, right, k max would be somewhere here, flat. This is called early stage of spinodal decomposition. This is a very early stage of spinodal decomposition. K max is independent of time. Then K max moves towards the left, and in fact one could identify this moving with a slope of a negative 1/3. K max, that is, the domains are growing with the time like a t to the 1/3 power law. This is called again this guy Landau, Schleier's dynamics, Landau, Schleier's mechanism. Basically, the droplets are coalescing, and some of them are breaking up, others are coalescing. When you look at that kinetics of association dissociation, you get this 1/3 law, and eventually it will become slope of -1. This is called hydrodynamic limit. People believe hydrodynamics is playing a role, because now we are talking about large length scales, and now the droplets are moving around, and the hydrodynamic flow is correlating all these things. So this is all experimentally verified. Okay, this is universal. The description here in terms of spinodal decomposition is universal. Any system, right? You can think of a birth of stars, right? In a galaxy, a bunch of stars, they grow, they die, all those things, right? Same thing. That's the way we try to describe them. Okay, so are you done? Is that okay? Now let's go.
Time dependent Ginsburg-Landau you are doing.
This is time dependent Ginsburg-Landau.
And time dependent RPA also.
Time dependent RPA also. Yeah, right. This is here time dependent TD-LG, time dependent Landau-Ginsburg. So I started with Landau-Ginsburg. This is a Ginsburg term. So as I mentioned, this was introduced by Ginsburg in the context of superconductivity, but interfaces are everywhere. Whenever you have interfaces, you must have that term, right? And it turns out the first person before Ginsburg, the first person who talked about this interfacial tension is Gibbs, of course.
1905 books.
Sorry?
When did he talk this?
That was in 18, I think I believe 93, Gibbs.
But he published his book in 1905.
Who?
Gibbs?
Willard Gibbs? Yeah, it takes a while to write the book. Yeah. You know, I don't know, this is a great place, right? This is this is a great place for mathematics, right? We call all this Ramanujan Hall, everything, right? Hardy, one of the mentors of Ramanujan, Hardy had said, young men prove theorems, old men write books. Okay, so he wrote the book much later. Okay, anyways, so let's go to the second part, and since we are kind of running late, but I want to complete this part. Is that okay? What time do you have?
I think we have to. Let's go on.
Can I finish this? So let me try to be brief. Okay, I'm going to erase this. Is that okay?
Just a small question. I thought that scaling 1/3 was named Lifshitz.
It could be. It's in the Lifshitz book, right? But
I think it's Lifshitz-Slavsov.
is it Lifshitz-Slavsov? It could be Lifshitz. Yeah, Lifshitz-Slavsov. Some people give credit to Landau and Lifshitz. Lifshitz wrote the book. People say it's a Landau. Doesn't matter. I'll make you happy. LLS, Landau, Lifshitz, Slavsov.
And this -1 scaling you see even in
CGI. Yeah, it's even in small molecular systems.
right. So even in the absence of fluid, right?
It's also what?
Even if the background fluid is, I mean, even in the absence of fluid, the scaling of
Yeah. Okay, right. And then the Lifshitz, there are brothers, two brothers. There are two Lifshitz. One Lifshitz is a great polymer physicist. The other Lifshitz is this guy. Okay, this is the older one. Okay, so let me go to the second. This is going to be again a very universal kind of thing. And I'm going to be, in the interest of time and also my perception, your background, I'm going to make it very simple. Okay, so here the mechanism is proposed that since it's a metastable, I'm quenching into metastable state. What does that mean? That means it still remembers that it was the previous thing, right? So in the case of spinolo decomposition mechanism, see here I started here, some fluctuations like this, and then some fluctuations like that, and then some fluctuation like this. Eventually that led to, right, a concentrated phase at phi double prime and phi prime. Okay, phi prime and phi double, very more complicated, the dilute is dense phase, right? That's what happens. In contrast, this is spinolo decomposition. In contrast, we are going to talk about nucleation growth. Right away, a daughter phase is born. The daughter phase has its equilibrium value. So in other words, you'll have one droplet here, another droplet there, another one there, another one there, another one there in the solution. Okay, and if I want to plot this density profile, this is concentration, then this is a droplet. This is spatial location, right? This is spatial location. It is one droplet with phi double prime, right? Another droplet with the same component, like a tiny one like this, and then a bigger one like this, right? On and on and on. They are being born randomly, and they are being these are nuclei or baby nuclei or embryos of the real phase, real equilibrium phase, in contrast to these simple fluctuations. Okay, so if that's the case, let me consider one such a droplet and see how that can be formed. Let's assume for simplicity, it's a sphere of radius r. Okay, and what is the free energy of formation of this free energy formation of this droplet? Let me write in kT. All right, in units for kT. And that's equal to, let's do it. The reason why this is formed is it's a thermodynamically favorable for it to form. That means it has a negative sign, and volume of this is 4/3 pi r cubed And what is the free energy gain in doing this? Let me write this to be a delta G, little g. And that delta G, yeah, of course, is related to, right, Tc minus the T, for example, T coexistence temperature, that is this temperature, right, this, suppose I quench it here, I quench it there. This is my T coexistence temperature according to the curve, but I am going down there. This is the temperature. So, T coexistence minus T, that is the driving force. This is positive, right? This is positive. And with a negative sign, that is the gain in free energy. This is the one that is responsible for formation or the birth of this nucleus. But whenever you do this, there is a problem, right? The problem is I have to pay a penalty to create an interface, because I am separating by force, I am separating a rich domain here and the poor domain there, right. So, I am creating this. So, therefore, there is going to be interfacial tension, and that is equal to 4 pi r square. Let me write interfacial tension with sigma instead of kappa. Okay. Very simple. This is really a high school kind of math, right. But the physics is very important. Now, let me plot this as a function of r, f over kt, kbt as a function of r. And let us do the same game again. When the interfacial tension is positive, we know that. When r is small, r cubed is weaker than r square. Therefore, this is going to dominate, and it is going to dominate so that this quantity is quadratic in r, positive. So, it is going to go like this. And eventually, for large r cubed is going to dominate over r square. With a negative sign, this is going to be strong, but negative. So, obviously, it is going to come down. Please recognize that I am writing this graph for free energy as a function of this nucleus. Previously, I had a curve like this one, that is with the rate of growth of fluctuations with respect to scattering wave vector k, right. There are two different quantities, except although they look similar. So, this means what? Suppose I make a baby nucleus with some radius r, right. To make her grow, it is going to be hard, because in order to increase r, I have to pay energy, I have to pay penalty, it is going to be hard. And if I go here, it has a tendency, suppose I made it has a greater tendency for it to go down, shrink, instead of going up. So, if I by fluctuation, suppose I make some drop